In this video, we cover a vertical freefall problem where I have a person throwing a rock upward from the edge of a balcony. So our initial speed here is 10 meters per second, and the initial height of the rock is 80 meters. And we're told to assume the acceleration of gravity is exactly 9.8 meters per second squared. I'm going to put an origin of coordinates here on the ground. So that's the point where y is equal to 0, which means the initial height of the rock is going to be 80 meters. Then we're asked in part A to get the flight time before this thing hits the ground, the landing speed, how fast is it going when it hits the ground. And then we have a little bonus problem in part C, assuming the speed of sound is 340 meters per second, how long after the crash does it take for the sound to get back to the balcony? So if I just quickly write down what I know and what I don't know here, I have the initial y value. I have the final y value because the rock lands on the ground. I have the acceleration, and I'm using an up is positive coordinate system, which means the acceleration of gravity is negative 9.8 meters per second squared. I also have the initial velocity, v naught is positive 10 meters per second. And then my unknowns here are the questions that are covered in part A and B. It's the time for the flight and then the landing speed, the final speed. So to go after the time, I'm going to use the first kinematics equation. Y equals y naught plus v naught y t plus 1/2 at squared. And my final y value is 0. I plug everything else in, and I get 0 equals 80 plus 10t minus, because a is negative 9.8, minus half of 9.8, that's 4.9, minus 4.9 t squared. And this quadratic equation requires that you either use the quadratic formula or use an algorithm built into a calculator or a computer in order to solve this thing. I'm going to show how to do this the long way. I prefer to have a positive a for the quadratic formula. So I'm moving everything to the left side of the equation. Add 4.9t squared, subtract 10t, subtract 80. Now in practice these days, I almost always use a computer to solve the quadratic formula, but I know a lot of you will be required to do this by hand, so I just wanted to illustrate it. So t is going to be negative b, which gives me a positive 10 plus or minus the square root of b squared, that's 10 squared, minus 4 times a times c, which is negative 80. All divided by twice a, which is 9.8. So when I'm doing this by hand, my preference is to just simplify the square root into a decimal, and then we'll figure out which solution we're going to keep and clean it up. So this gives me 10 plus or minus 40.8, all divided by 9.8. And we're going to keep the positive solutions. So that's when I go 10 plus 40.8. The other solution is negative, which would be a time before the actual physical process began. So we're throwing that one away. And I get an answer to 3 sig figs of 5.18 seconds for the flight time. Then I get into question B. And there's a couple approaches to this. If you remember the third kinematics equation in our lists, that could get you the final speed by plugging in things that were originally given in the problem. But the other way to do it, now that we have the time, we could go back to this more fundamental kinematics equation, which is my preference, that the velocity is given by the initial velocity plus acceleration times time. So my initial velocity was 10 meters per second. My acceleration again is negative 9.8. The time for the process, 5.18 seconds. I can follow the units here and verify that I get meters per second. And to 3 sig figs, I get negative 40.8 meters per second. Now notice that's not technically the answer to the question, because the question was, what's the landing speed? And that's just the magnitude of the velocity vector. So I can just erase my minus sign because I'm just talking about how fast, not what direction. And I'm being a little ambiguous with my notation here, but I'm writing a v now to stand for the magnitude of the velocity vector. Now in part C, the physics all changes. The rock has hit the ground. It's going to make sound waves, travel back up to the person who originally dropped it, and those sound waves are moving with a constant speed that I'll call Vs equals 340 meters per second. So the problem no longer involves any acceleration. It's just a constant speed problem. And this goes all the way back to distance equals rate times time. If you wanted to be formal about it, I could write down the first kinematics equation. But now I'm describing the motion of the sound waves, and they move with a constant speed, which means zero acceleration. Their starting position happens to be 0, and I end up with this simplification of the first kinematics formula, y equals the initial speed, because that's a constant, times time. And this is just distance equals rate times time. So to find the time, I just divide by that speed of sound. I'll call it Vs now, and I get y over Vs. And keeping 3 sig figs, I get 0.235 seconds. In some versions of this problem, you're asked for the total time that it takes to hear the crash of the rock into the ground. So you would just take the travel time for the sound and add it to the travel time for the rock to get to the ground, and you get the total time. Into 3 sig figs, that comes out to 5.42 seconds. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.